Welcome everyone, good morning. Welcome to our Physics for Everyone program. My name is Jan Schemla. I'm the Associate Head for Undergraduate Programs here in Physics. And I'm filling in for Irene Lira-Ansager, who's normally the coordinator for this program, but she had to be away at a conference. So we're really excited to be back in person. This is the first time we've done this in a few semesters because of the pandemic. We were on hiatus. So it's great to see all these people here in person. This is the second talk of our series, and we're really lucky to have Professor Charles Gammie here, who's going to tell us about his group's research. So Professor Gammie received his PhD from Princeton in 1992, and then did a postdoc at the University of Virginia, and then at the Harvard-Smithsonian Center for Astrophysics, and has been here a faculty member at U of I since 1999. And as he's going to show you, his lab does research on black holes and other stellar objects. And we're really excited to hear him talk. So one thing about the format of these talks, Professor Gammie is going to talk for about an hour. He's actually encouraging people to ask questions during the talk, but also we'll have plenty of time after the talk, 10 to 15 minutes or so to ask questions. Okay, Charles, you can take it away.
Thank you. Can you hear me okay? Okay, great. Dave, hi. As Jan said, I study black holes, and I'm going to talk about a portrait or an image of a black hole that my group was involved in making over the course of the last year. This is a portrait of a black hole. This is produced by an AI from a description, a verbal description that was offered. But I'll show you a real picture shortly. So I think many of you have seen this picture before. Have you? Has anyone? Okay. Okay, great. It's an orange donut. And it's a little unfortunate. There was a donut shop that doesn't have a outlet here in town that offered free donuts when this came out. So this came out in May, so almost exactly 5 months ago. And this is an image of the black hole that lies at the center of our galaxy, the Milky Way galaxy. I'll try and explain to you what you're seeing in this image and how it was made and what you should believe about the image. Yes?
So are we seeing it top, bottom, or edge on?
That's a great question, and that is a topic of current research. Yeah.
Could you repeat the question?
Oh, the question is, are we seeing it top, bottom, or edge on? And we don't, so we know we're not seeing it edge on, I think, now. But it's a topic of current research, exactly what the orientation of the black hole is. It's not actually obvious what you mean by the orientation of the black hole, so I'll say a few words about that, but I'll get there. Well, that is also an open question. Right, so the question was, is it spinning? And we'll get to that as well. So just give us a little time. Okay, so this is the second of 2 black hole images that have come out. So here's both of them together at the same angular scale. The one on your left is a black hole at the center of the galaxy, M87. And the one at the right is the one that at the center of our galaxy, which is also known by its radio source designation, which is Sagittarius A star. So it's in the constellation Sagittarius, and it's the brightest radio source in Sagittarius. So I've got a little bit more information up here about each of these sources. They're at very different distances from us. So the one on the left, the M87, is a black hole that we believe has a mass of about 6 billion times the mass of the sun. And it's in a galaxy it's not right next door, but it's sort of in our cosmological neighborhood. And this is one of the biggest black holes in the universe. So it turns out that the size of a black hole, measured in meters, is proportional to the mass of the black hole. So a bigger or more massive black hole has a larger size, and this one is about the size of our solar system, a little bit bigger than the orbit of Pluto. The one on the left is, again, the one at the center of our galaxy, and it's about 4 million times the mass of the sun. So about a little over 1,000 times less massive, and therefore a little over 1,000 times smaller in size. So it's somewhat bigger than the sun. So if we replace the sun with this black hole, we would see something sort of about this big on the sky. And it's one of the smaller black holes that sit at the center of galaxies in our universe. So we live in sort of we live in Champaign-Urbana. But our galaxy is sort of the Champaign-Urbana of galaxies. And M87, which is the galaxy that this other black hole is in, is sort of the Chicago. Okay, so these both have about the same angular size on the sky because the black hole on the left, about 1,500 or 2,000 times bigger, is also 1,500 or 2,000 times further away. So it subtends the same angular size on the sky. And it's a little bit of a miracle that both of these things are about the same size. They're just at the very limit of what we can see. And it's just a miracle that they're just big enough to see. Did you have a question?
Does the size of the galaxy depend on the size of the black hole?
So the question was, does the size of the galaxy depend on the size of the black hole? I would say, again, that is a topic of current research. But there's not a clear one-to-one relationship the way there is between the size of the black hole and its mass. But there is a correlation between the mass of a galaxy and the mass of the central black hole. And the two tend to be related by maybe a factor of about 10,000. So maybe a few thousandths or a few tens of thousandths of the mass of a typical galaxy is in the central black hole. But there are exceptions. There are galaxies with enormous black holes, and there are galaxies with very small black hole or no black hole that we can detect. Yeah?
Were these images taken with the Webb telescope?
Okay, good. So the question was, were these images taken with the Webb telescope? And the answer to that is no. So Webb doesn't have the resolution to see these black holes. So I'm going to talk next about, that was a great segue, thank you, about the technique that was used to make these images, which is called interferometry. So, and there it is. There's no camera that's used to take these images. There's a set of radio antennas that are spaced around the globe. And they're not ordinary radio antennas like the ones that you use to get your satellite TV. They are millimeter wavelength antennas. So they're very, very high frequency antennas. And their signals are combined in a special way to make an estimate of what these things look like. So let me show you, I'm going to show you in just a moment a brief movie of this. And what you're going to see is the Earth turning as seen from the center of our galaxy. And you're also going to see on the right-hand side of this an image of a teapot that has been reconstructed using the techniques of interferometry. So it turns out that as the Earth turns, we get more and more information about the source, and we get better and better at reconstructing the image. Okay, so the telescopes, the antennas that were used to do this research are antennas that were built for other purposes. They are antennas that operate at a frequency of 230 gigahertz. So just to put that in perspective, your microwave oven is like 5 gigahertz. Okay, so this is way, way above the frequency used in your microwave oven, and way, way above the frequencies that are used on cell phones and ordinary radar and so on. And the associated wavelength of the radiation is about 1.3 millimeters. So people talk about this being millimeter astronomy or sub-millimeter astronomy. Okay, so it turns out that the resolution that you can achieve, the angular resolution that you can achieve, is proportional to the wavelength of the radiation that you're observing at divided by the diameter of your instrument. And this is one reason why people like to build big telescopes. You get a bigger diameter, and so then the angle that you can resolve is smaller and smaller, the bigger and bigger the instrument. Here, when we combine signals from different antennas that are spaced as much as 2 Earth radii apart, so on opposite sides of the Earth, the effective size of our telescope is the size of the Earth, and the wavelength is 1.3 millimeters. So let's see, is there a pointer here? Okay, so you can see I've done the calculation for you up there. You can take the wavelength, 1.3 millimeters, and divide by 2 times the radius of the Earth, which is about 12,800 kilometers, and you get a number. And that number is the angle that you can resolve in radians. And then you can convert that to a unit that astronomers like to use, which is micro arc seconds, okay? And that gives you that number over there at the right, 25 micro arc seconds. That's what we can resolve using these telescopes spaced around the globe. Okay, so how is this done? So what happens is that the people in my collaboration, so not me, I'll tell you what we do in just a moment, but other members of my collaboration go to these telescopes, and they carry with them a rack of electronics. And the rack of electronics includes a very accurate clock and many, many disk drives. So a whole stack of disk drives. And one of the things that makes this experiment possible is that disk drives are now very, very cheap. So if we'd had to buy all these disk drives in the year 2000, it would have broke the bank, or at least would have broken the NSF, National Science Foundation. So we record using the clock and the disk drives. We record the voltage stream that comes off the telescope. And then once the observing campaign is over, take the disk drives out, carry them by hand back to a central facility. There's actually 2 central facilities that do this, one in Massachusetts and one in Bonn in Germany. And then we compare the signals at pairs of telescopes. And what you're searching for in these signals from pairs of telescopes is a time offset between the arrival time of the signals at individual telescopes. So you're doing sort of a triangulation, right? You could do this with thunder, for example. If you could hear thunder at the western edge of town, sooner than you hear it in the center of town, you would know that the lightning strike occurred in the west. Okay, and here we're doing a very similar thing, but with light, and at very, very high accuracy. Okay, so that tells us something about the structure of the source. And now I'm going to get a little bit technical. The actual thing that we're measuring is what's called a Fourier component of the source on the sky. And let's hold on just a minute. And I'm going to go through this video first. So we measure what is effectively a wave component in the brightness on the sky. And then we add these wave components together to infer an image. Thank you so much, Sean. So let me turn on the animation. And you'll see pairs of telescopes linked up by a line on the map on the left. And you'll see the beginning of the reconstruction of an image of a teapot on the right. Does anyone know about Russell's teapot? Okay, you can. So that's what this is based on. Okay, so you can see we get linkage between our telescope at the South Pole in Spain, and then another telescope in the Atacama Desert in Chile, another in Mexico near Veracruz, another in Arizona, and more on the top of a volcano on the Big Island in Hawaii. These are all high dry sites, and they need to be high and dry so that we're above most of the atmosphere and most of the water in the atmosphere in order for these high frequency telescopes to work. Okay, so you can see that as the Earth turns, as the world turns, if anyone's a fan of 1970s soap operas, we can begin to reconstruct an image of a teapot. Okay, so in this particular image, we're doing this with 8 telescopes at 6 separate sites. So some of our sites have multiple telescopes for redundancy. And again, all of these telescopes were built for other purposes. One, in the Atacama Desert in Chile, is the most important of all of these telescopes. It's known as the Atacama Large Millimeter Array, or ALMA, and it's the largest telescope in the network of telescopes and gives us most of our signal to noise in the image. So you can see that after all this, you can begin to put together something that looks like a teapot. But you should also be able to see here that we're not just taking a picture and we have to guess at what the image looks like. And in particular, this teapot on the left is not a unique representation of the data. So there are other possible images that are also consistent with the data. And we've done a lot of work to try and make the best possible guess as to what the image looks like. And people always ask about this. You know, it's not like taking a picture with pixels and then photoshopping it. And in fact, I did an interview where the host said, "Now tell me for real, is this image photoshopped?" You have no idea. There's millions of hours of core hours of computing time that go into transforming these signals received at pairs of telescopes into something that we think is the best representation of an image of the source. Now I'm done. Your question. I'm not sure. So the question was, how much data do we collect? And the total amount of data for this run was about 5 petabytes. So it's a good fraction of a petabyte per site. It's not exactly the same at every site, and there are other corrections, but it's a lot of data. Yeah.
The slide says there were 6 targets, including the 2. Anything interesting from the other 4?
Yeah, they're interesting, but they're nowhere near as interesting. And the reason is that we also pointed at systems where the black hole is much, much smaller. And so you see things around the black hole, but you can't resolve the black hole itself. Yeah. Okay, so that's how we do this. So now I'm going to show you a propaganda video produced by the European Southern Observatory. And this starts at ALMA, this big telescope in Chile. This is an international observatory funded partly by national agencies in Europe, the US, and in Asia. And it consists of a whole bunch of millimeter wavelength antennas sitting in the desert, one of the driest spots on Earth, other than the South Pole, actually. The South Pole is incredibly dry. And what you're going to see is we'll look up into the sky and zoom in on the center of our galaxy. So there's Sagittarius, constellation Sagittarius. And then we zoom in and look at the very center of the galaxy. And I'm actually going to go through each stage of this a little later in the talk, but this will give you a sense of how fine the resolution of this project, this Event Horizon Telescope it's called, how fine the resolution is. So these are some stars near the black hole. And then we zoom in on the black hole itself. And there it is. All right. Yeah?
What that image actually is showing us is it radiation receiving from the actual surface of the black hole or something that's slightly around the black hole itself?
Okay, so I don't know if people heard that, but the question was, are we seeing radiation from the black hole itself or from things that are near the black hole? And I'm just about to do that piece of the talk, so thank you. But the short answer is it's from things that are near the black hole. So we don't see any radiation from the black hole itself. That's the defining feature of the black hole. Okay, so this is what we see, and there's the next header in the talk. What are we seeing in these images? Okay, so what we think is going on is that there's a black hole in here which is completely absorbent of light. So we don't see any light directly from the hole. And it's got gas that's around it. And the gas is at a temperature somewhere between 1 billion and 1 trillion Kelvin. It's really, really hot. And that gas is swirling around the black hole and giving off radiation through a process which is called the synchrotron process. And synchrotron process is where you have a magnetic field and you have charged particles that orbit in the magnetic field. So they spiral around magnetic field lines. And as they spiral, they're accelerated. And it's a basic physical fact that accelerated charges radiate. And these happen to radiate mostly at a frequency close to that that we use to observe this black hole, so close to millimeter wavelengths. Okay, so what my group does is state-of-the-art simulations of this process. So I'm going to show you a state-of-the-art simulation that we've put together at great expense and great effort. And this shows some kids at Uni Primary School out there who helped us out and asked lots of good questions about black holes. And you can see up here we're on the Uni Primary Playground, and the kids are holding a black cloth in the middle, which is meant to represent the black hole. And then you can also see the kids, here I'll start this up. The kids are running around the black hole, and this represents the gas. It's mostly hydrogen and helium that is circulating around the black hole. And the closer in you get, the faster they seem to move around. And the ones on the outside are moving a little bit more slowly. And then every once in a while, something gets tired and accretes onto the black hole. Yeah, there we go. There's an accretion event. So this is what we think is happening to this really, really hot gas around the black hole. It's swirling around the black hole. Some of it's falling in. And as it falls in, it gets hot and it radiates. And that produces this millimeter wavelength radiation that we see. Okay, so this particular movie was taken from a drone that was hovering above the playground by one of my graduate students. And in this movie, light travels in a straight line from the students to us. Okay, but when you're close to a black hole, light no longer travels in a straight line, and it's bent, it's deflected by the gravity of the black hole. So I have a little illustration of that here. So telescope is over here. This is where we are looking back at the black hole. And on lines of sight that pass far from the hole, so if we look away from the center of the hole off to one side, those lines of sight are represented by this line right here. Here's the black hole. So as we trace back along those lines of sight, you can see it's bent by the gravitational field of the black hole. So this happens even in our solar system. So this happens to light that goes by the sun, but it's a very, very small effect. So this small effect was one of the famous early predictions of Einstein's theory of gravity, general relativity. And there was an expedition during an eclipse to detect this, and it made the front page of the New York Times when it was seen. But here, instead of a very tiny deflection, as we see close to the sun, stars moving with lines of sight close to the sun, this is a detection of, deflection of tens of degrees. Okay, now even more remarkable is that when the line of sight gets closer and closer to the black hole, it gets deflected more and more. And eventually, there's something called a photon orbit here that's quite close to the black hole. And so on certain lines of sight, you actually wind up almost on this photon orbit, where the photons just sit there and run around the black hole like a satellite running around the Earth. Okay, but one crucial difference between satellites around the Earth and these photons running around the black hole is that these orbits are unstable. And so the photons can't sit there for very long. They either go into the black hole or they go away and escape to large distance. Okay, and then if you look even closer to the center of the black hole on an image that's represented by these lines of sight, then your line of sight ends on the horizon. And that produces what we call the black hole shadow, which is the dark patch in the center of that orange donut. Okay, so that's the shadow of the black hole. All right, so what we do actually is create state-of-the-art simulations. And I'll show you some of our simulations of M87 on the left and of the center of our galaxy on the right. And you can see that they're evolving at very, very different rates. So the black hole in the center of our galaxy is relatively small, and things move around it at close to the speed of light. And so it evolves very quickly. And then the black hole in the center of M87 is very, very big and evolves at a stately pace. Okay. So this is what comes out of our supercomputer simulations of this process. And this is the Illinois contribution to understanding what Event Horizon Telescope sees. Unfortunately, this is not what is actually observed. So what's actually observed is something more like this. Okay, so it's blurred by a combination of the instrumental resolution. So, lambda over d, the wavelength of the radiation divided by the size of the Earth, is as fine as we can see. And we can't put telescopes off the Earth yet, although we hope to do so, and get finer resolution. So this is the best we can do at the moment. Yeah, you had a question. The question was, is there a black hole at the center of every galaxy? And the answer is almost certainly yes. Yeah. There may be a few that have lost theirs, but we think that almost every galaxy has one at the center. And certainly every nearby galaxy. Yeah?
The square root of 27 is unusual in that formula. Any insight where that comes from?
Yeah, well, it comes from the orbits of the photons, and this is something that our students work out in their first graduate course in general relativity. And there's no, I don't have a cute explanation for you of, why it's root 27 and not root 28 or root 57, but that's just what it is. Yeah. Okay. Yeah. I'm coming to that. Yeah, I'll talk about that in a minute. Okay, but before we get to that, so our group does simulations of these things, and you can see this is what the simulations produce, and this is what the observations produce, and they're pretty close to one another. We're pretty happy with the simulations being able to predict what we see, with some exceptions. So I love this quotation from Feynman because it sort of runs contrary to some of the salesmanship we see in physics these days. But the people who put together a theory are the people who understand its flaws the best. And so I want to explain to you some of the things that we don't understand in these simulations. And one thing that we really don't understand has to do with the black hole at the center of our galaxy. So we can monitor the millimeter wavelength radiation coming from the center of the galaxy, and it varies on our timescales. So it goes up and down by typically 8% over a timescale of a few hours. And our simulation should be able to reproduce that. And when we go and try and reproduce that, we find that our simulations go up and down by about twice as much every few hours. And we don't understand why that is. We have some ideas, but there's a bit of a mystery. The mystery is probably not answered by fundamental new physics. It's probably not that there's some sixth force that is unknown to physics that's reducing the variation in light from the galactic center. It's more likely that our models are just a little too simple and don't include all of the physics that we know because it's too expensive to calculate. Okay. But it could also be that there's something fundamentally wrong with the black hole model as well. And that's something that is unlikely, but is something that we really want to go after. Okay, so the models work pretty well. We pretty much understand what's going on. We can explain most of the data, but there are still some flies in the ointment. Yeah. I'm saying this a lot, but that is a topic of current research. So what's going on in the center of the galaxy, we think, is that there are stars orbiting the central black hole, and stars have winds. So our star the sun has a wind. It's a very, very faint wind. And it's such a faint wind that it doesn't significantly change the mass of the sun over the entire lifetime of the universe. But the stars that are close to the black hole in the center of our galaxy are giving off very strong winds. And they're sufficiently strong that it'll change those stars over a timescale which is sort of order the lifetime of the human race. So millions or tens of millions of years. And that gas flows off, and then some of it gets close to the black hole and swirls in and is captured by the black hole. And it's an open question whether or not we need to model all of the flow of gas all the way from the stars down into the black hole, or whether we can just focus on what's going on around the black hole. It turns out that people have done both those things, and neither of them fully explain the data. But it seems likely that the models that include the stars that are feeding the black hole would do a little bit better. Okay. So let me just talk about the center of our galaxy a little bit more, and then we'll get to future prospects. Okay, so what's going on in the center of our galaxy? So if you look up in the night sky, this is what you see. So this is what we call an optical image of the galaxy. And if you look up here, the horizon will lie roughly like this across the image, and the center of our galaxy is way down on the southern horizon. And we sit inside this galaxy. This galaxy is like a frisbee, and we're sitting inside it, looking through a disk of stars toward the peak in the concentration of stars close to the center. And then on top of this image, you can see, there's all these bands of darkness superposed on the light. and that is what astronomers call dust. So it's not household dust. It's something like soot, little micron-sized pieces of carbon and silicon that block the light from stars. And if you look into the center of our galaxy, you can hardly see the center of the galaxy at these wavelengths. In fact, you cannot see any light from the stars that are close to the central black hole at these wavelengths. But if you go to longer wavelengths, if you go into what's called the infrared, then you can see through some of this dust. And to do that, you might use the Spitzer Space Telescope, which is a sibling of the Hubble Space Telescope that works in the infrared band. And this produces a picture of the center of the galaxy that looks like this. And you can see that the bands of absorbing material are much fainter in this image than in the optical image that I just showed you. Okay, so let's see. Oh. So there's the optical image, and then we zoom in on the center, and you can see that a lot of the obscuring dust is no longer visible. Okay, and then all this light here is coming from stars. So there are just so many stars on this image that we don't see them individually. We just see a peak in the brightness of stars close to the center of the galaxy, which is right there. Okay, now you can zoom in even further in the infrared using big ground-based telescopes, like what's called the Keck telescope on Mauna Kea in Hawaii. And this is something that Andrea Ghez did. So she's a person who spent her entire career looking at the center of our galaxy using this Keck telescope in Hawaii. And she finally won the Nobel Prize for her work a few years ago. And what she has been able to do is make a movie of stars that orbit the central black hole. So I'm going to show you the movie. And this movie is the product of decades of work, repeated visits to the telescope to take pictures of the distribution of stars close to the center of our galaxy. And now we can see individual stars because the stars that she is seeing are very, very bright, and there aren't very many of those close to the center of the galaxy. Okay, so here's the movie. And it's amazing. You can see things moving. You can see where the black hole is in this image, right? Where things are moving very, very quickly. We don't usually expect to see things move on the sky, other than the planets and moons around planets. But here, you can see that there's one star in particular, which they've designated SO-2, which circulates in a little ellipse around the black hole, which is here. And Ghez was one of two investigators who pursued this work. The other was a guy named Reinhard Genzel in Europe at the Max Planck Institute. And Genzel and Ghez won the Nobel Prize together for this work. Genzel used a different telescope in Chile, so European Southern Observatory in Chile. Okay, so from this, from monitoring the orbits of stars around the center of the galaxy, it's possible to deduce the distance to the black hole, and it's also possible to deduce exactly what the mass of the black hole is, to within a few percent, which is really remarkable. And as I mentioned to you, the size of the black hole is proportional to the mass. So with the data from Genzel and Ghez, by monitoring these stars, we're able to predict exactly what the mass of the black hole is, and therefore what the angular size of the black hole should be. Okay, so we had a very clear expectation going into these observations of how big that donut should be on the sky. And that was exactly what we saw. So to within about 20%, and that's all error, the size of this ring is consistent with what's expected from the Genzel and Ghez data. Okay, and this zooms in even further than Genzel and Ghez were able to, because the resolution of the Event Horizon Telescope is much greater. This is one of the finest images the highest resolution images ever made. Okay, so what comes next? What is the future of black hole imaging? What should you watch for? So there are lots of plans to build on past successes, and almost all the plans involve vast expenditures of money. Okay, so many of these may not happen. But in the near future, we've been able, or actually in the recent past, we've been able to add additional antennas to this network of antennas that made the observations that made those images. And so those images were made by 8 telescopes. So now there's a new telescope in the Alps called NOEMA that is contributing to the Event Horizon Telescope. It's participating in the campaigns. There's another telescope in Greenland at the Thule Air Base, which was built by a combination of funds from Taiwan and from the Smithsonian Astrophysical Observatory, which means you. And there are also new telescopes in Arizona that are contributing to these images. Okay, so in the future, there will be more pairs of telescopes that can be used to make that teapot image. And those pairs will produce a higher fidelity image. So we won't have to guess so much about what the image looks like. So better images from more antennas. And there's also a plan to put together something called the Next Generation Event Horizon Telescope, which will add yet more antennas, including one that's planned to be built by Europeans on a mountain in Namibia that is owned by the Max Planck Institute. So there's a high mountain in Namibia that already has electricity and a road to the top of the mountain. And it's a good dry site where it makes sense to put a millimeter wavelength telescope, which will be known as the African Millimeter Telescope. Lots of other harebrained ideas that have been considered, including putting telescopes on balloons, and as I'll get to in a moment, putting telescopes in space. But these are fairly modest investments. So African Millimeter Telescope will cost something like $10 million, which on the scale of large scientific experiments is not that big. Okay, so better images, more antennas. You'll also have seen that the galactic center black hole in the simulations evolves over time. And what we hope to do also is go back and take a series of images and make a movie of the black hole. And that is also something which is in progress and is likely to happen in the very near future. Okay. Next advance is also already underway, and that has to do with the instrument's resolution. So I said early in the talk that the resolution is proportional to the wavelength of the radiation that you're observing at divided by the size of the instrument, which is 2 times the radius of the Earth. Okay, we can't change the radius of the Earth, but we can change the wavelength we observe at. But we're restricted because we can only observe at wavelengths where the atmosphere is transparent. And there's a limited set of windows in the millimeter where we can do this. So 1.3 millimeters, where we operate now, is one of these windows. There's another window at about 0.87 millimeters. And efforts are underway to put a new set of receivers on these telescopes and to make them capable of observing at 0.87 millimeters. So that'll increase the resolution by about a third over what we can do now. Okay, so I said we couldn't change the size of the instrument, but we can certainly do that by going to space. But putting an antenna in space costs about $1 billion. And in anybody's book, that's real money. And so there are lots of proposals to do this. Some of the proposals involve building a special purpose satellite to do this. That's the $1 billion price tag. Other proposals, including one that I'm involved in, involve hitchhiking on another satellite. And that's a fairly small increment in expense. And the instrument we want to put up is called MOVIE, and hitchhikes on a satellite called Saltus. If you do this, you can change the baselines. And so that lambda over d, the d becomes the distance between the satellite in orbit and an antenna on the surface of the Earth. And so you can get much higher resolution. Our idea is to put this satellite in an orbit that goes about halfway to the moon and then comes back. And so that significantly, by a factor of more than 10, increases the resolution of the instrument. Yeah? It would be really expensive. It's not cheaper than putting something in orbit, for certain. Also, it's not clear that you really want to do astronomy on the moon unless you're really just looking for something to do on the moon. Because one of the problems that large antennas face is gravitational deflection. Okay, so you may have seen pictures of large astronomical radio antennas on Earth. And when those things shift their focus, when they point at a new source, the entire instrument has to turn. And then the shape of the instrument changes due to gravitational deflection. Right? And that's something that has to be engineered around. So the antenna has to be built either stiff enough to correct for that, or it has to include special purpose motors that reconfigure the surface to compensate for the gravitational deflection. And that deflection is still there on the surface of the moon. But if you go into space, it's not there at all. It's wonderful. So you can point someplace else, and you don't have to refigure your instrument for gravitational deflection. Okay, any other questions on that? Yeah?
So you were saying on number 3 that a higher resolution that you only allow certain windows of
Yeah.
what to do because of the Earth's atmosphere.
Yeah.
In your space, that's no longer the case. Can you get data from space that is better because the resolution is at a different wavelength and combine it with what's on Earth and then still create, a multi-data output? Or are you looking at two different things that way?
So the idea is to put an antenna in space. It functions just like another millimeter wavelength observatory on the Earth. So it connects to pairs. It pairs up with instruments that are on the surface of the Earth. And you correlate the signals at the two antennas, so one on the Earth and one in space. You could go, yeah, so you have to do, both antennas have to operate at the same wavelength. Yeah. And you could go to a shorter wavelength in space. So as you say, you're not limited by the Earth's atmosphere. But then you might have to fly 2 or 3 or 4 antennas in space. So then you're talking about $2 or $3 or $4 billion. Yeah. Yeah, that's right. So there are ways to sort of edge around this. So people can now do what's called phase transfer, where you observe at 2 frequencies simultaneously, but that will still not allow you to operate at one frequency in space and a different frequency on the ground. Yeah. Okay, so higher resolution, and then the thing that I'm most excited about, which is better models, so bigger computers. And right now we use the largest available supercomputers in the world. So we're using a computer called Summit, which is at the Department of Energy's Oak Ridge National Lab. And very soon, there will be even larger computers available to researchers like me to produce better models. Okay, so that is it. And I am happy to take questions. Okay. Yes, and then here, and then here.
Charles, do you want us to pass the mic around for people in the audience, or? Okay. I'll be around with my microphone available if somebody wants it. Then.
The question I have is, how do you even figure out where one is? I mean, universes are pretty big, so how do you even figure out where a black hole is?
Yeah.
How do you even find one?
Right, how do we find these? So actually, I have a slide that may help with M87. So let's, oh, I don't have that slide. I have it somewhere else. Let me bring this up. Okay, so this is a talk I gave last week in Vanderbilt. All right, so this is the galaxy M87, and this is an image of M87 that was taken with Hubble Space Telescope. And this is one of the largest galaxies in the neighborhood of our galaxy. And it's at the very center of a cluster of galaxies called the Virgo cluster. And we think that the black holes in galaxies like this are always in the center. And that helps a lot. So there's a process called dynamical friction, which was discovered by a guy named Chandrasekhar, who worked at University of Chicago for many years and was also a Nobel Prize winner. And this dynamical friction process causes a black hole that's placed outside the center of the galaxy to spiral into the very center where the stars are densest. Okay, so I think that's the basic answer to your question. But then in addition to that, in the case of M87, you can see there's stars there. There's sort of an orangish background that peaks up close to the center. But there's also a little stripe of light that comes out of the center. And this was first noticed by an American astronomer named Heber Curtis in 1918. And he just made a little note in his paper, said, you know, there's something interesting going on in this galaxy. And nowadays, we know that this is a jet of plasma that's coming out of the center of the galaxy and actually emerges from very, very close to the black hole. So this plasma that's circulating around the black hole couples to the black hole's gravitational field, and that causes the black hole to spin down. So someone was asking about spin earlier. So there's an idea that black holes have spin. They spin just like the sun rotates. So the sun rotates about once a month. Black holes also are believed to rotate. And they act like a giant flywheel that stores energy. And you can tap into that energy using electromagnetic fields, especially magnetic fields. And that is believed to produce the jet that's seen here. So wherever you see one of these jets, you can probably follow it back and find a black hole at one end. So that's another way we find black holes. But the basic answer to your question is they're there at the center of every galaxy. Okay, so I think you're next, then we'll, yeah, okay, so. Oh, no, I was gentleman in the orange shirt, and then we'll come to, yeah.
If I interpreted a couple of different things you put together, what we're actually seeing in that donut is an image approximately the size of the sun.
A little bit bigger.
A little bit
Yeah.
on that scale.
Yeah. Yep. Okay, and then you were next.
Can black holes merge?
Can black holes merge was the question. Yes. And we know that they merge because we detect ripples in the gravitational field that are set up by the mergers.
So will the universe end when we all merge into a single black hole?
We will never know. So the people have this idea from, if you're like me, you saw the Disney video, The Black Hole, in the 1970s, right? So it's sucking in everything around it, like a hungry animal. And black holes don't really operate like that. So, to give you a sense for what happens to the gravitational field, if we took the sun and we compressed it into a black hole, it would be a few kilometers in size. And if we just did that, the orbit of the Earth would not change at all. And the Earth would never get sucked into the black hole. Okay, so the gravitational field of a black hole only differs from that of a body like the sun very, very close to the black hole itself. Okay, so I think you were next, and then I'll come down to you.
In our galaxy, is the dark matter uniformly distributed, or is there concentration of the galactic center?
Okay, so the question was, in our galaxy, is the dark matter uniformly distributed, or is it concentrated in the center of the galaxy? And that's a matter of current research. So first of all, the premise of your question is that there's dark matter in the galaxy. And so some people may not know that only part of the matter content of our galaxy is in the form of stars, like our sun. And much of the rest of it, probably the majority of the mass, by factors of many tens, is in some mysterious dark matter, which is, the best bet is it's some kind of particle that only interacts very, very weakly with all other kinds of particles and with light. And that's why it's called dark matter. And it's likely that that dark matter peaks up somewhat toward the center of the galaxy. And it's possible that it peaks up right around the black hole, which is something that some of my colleagues have written papers about. So Stu Shapiro here in this department has worked on that problem. But because the dark matter has not yet been detected, those particles haven't been detected yet, we don't know what it is, then we also don't know how it behaves in the presence of the galaxy's gravitational field, and we don't know whether it peaks up at the center or not. Okay, and then you, and then you, yeah.
So your images,
Okay,
your images including the teapot were all orange.
yeah.
This is radio astronomy, but are you guys approximating what we would see in a visual field, or is this like a heat signature, or what would you see if you were like floating outside a black hole looking at that scene?
Okay, so I have a bunch of things to say about that. But basically, it's just a color map called AFM hot that people in the collaboration thought looked cool. Okay, but it is true. Actually, it's kind of the opposite of what's really going on. So things that are blue tend to have more light coming out at short wavelength than at long wavelength. And things, by contrast, that are orange thank God our colors are orange and blue. Things that are orange have more light coming out at long wavelength. And in these sources, we tend to see more light coming out at short wavelength than at long wavelength. That's just the slope of the spectrum where we observe it. But also, people thought it was cool, but there were also endless Zoom telecons over, we need a perceptually uniform color map, and worrying about what would go into those images, because the image of M87 was eventually seen by, we think, 4.5 billion people. So it was prepared fairly carefully. Yeah.
Two questions, one straightforward, one very hypothetical. Is Hawking radiation included in any of the models? That was the straightforward one. The other is...
Okay, then let me answer that first. And the question was, is Hawking radiation included in the models? Okay, so you may know that one of Hawking's contributions was to identify something called Hawking radiation that occurs close to black holes. And this happens even for a non-rotating black hole. So one that we can't get any energy out of a non-rotating black hole. It's not a flywheel, it's a flywheel that's sitting still. And Hawking's idea was that all the time, the vacuum is producing particles and antiparticles that appear and disappear. And then every once in a while, you make a particle and antiparticle, and one of them gets cast into the black hole. And so the other one becomes real, so it can't disappear anymore. And then that particle runs away from the black hole, and that's what Hawking radiation is. Now, when Hawking did this calculation, he assumed that the black hole was surrounded by nothing, that it was in vacuum. Whereas real black holes in astrophysics are surrounded by radiation. I mean, there's light from the Big Bang that's left over that permeates space and gives you static on your old television set, if you still have one, to turn on. And there's also gas all over the place. And once you include all that, Hawking radiation is completely suppressed. So Hawking radiation doesn't matter for the kind of black holes that we look at. There are some black holes that are hypothesized to exist for which it may matter. And those black holes are very, very small black holes that might have been made early in the lifetime of the universe. And they tend to Hawking radiate much, much more strongly than these black holes. So, no Hawking radiation. So we don't include it.
The second very hypothetical question is, if a black hole the size of M87 happened to be in the center of our galaxy, would the radiation from that be inimical to life at our distance?
So the question was, if we had a black hole that's as big as the one in M87 at the center of our galaxy, would the radiation it produces be dangerous for life? And I think the answer to that question is no, although I don't think anyone's done that specific calculation. So the brightness of the black hole in M87 is about 1 billion times the luminosity of the sun. And there are about 10 billion stars in our galaxy. So it wouldn't be as bright as the sum of all the stars in our galaxy. So I don't think it would do that much. Now, having said that, there are black holes of similar mass that have much more gas falling into them and are much, much brighter. And those guys produce a lot of radiation. They're brighter than their entire host galaxy. And those might be inimical to life. And this is something, there's a whole other strain in astronomy concerned with finding life elsewhere in the universe and studying exoplanets. And people talk about what's called the habitable zone, the galactic habitable zone. So if you're too close to the center of our galaxy, there's lots of stuff happening. There are supernovae going off, and those can be dangerous. Those can sterilize a planet. And the notion is that we're far enough away from the center that hasn't affected us yet. Although it's just a roll of the dice. Life is a crapshoot. And it could be that a star will wander by 10 million years from now and go boom and sterilize the Earth. But it's unlikely. Yeah. OK, you had a question? Then we'll get it. Yeah. Yeah.
I'm guessing that if the black hole were to emit or give radiation, it would, heat transfer is the radiation. Is there some type of heat transfer in the black hole, or does it, if yes, does it emit it or does it give off radiation?
Yeah. So part of the question was about how energy is transferred away from the black hole. And in intro physics, we say it can happen by radiation, which is certainly going on here. And the energy there is coming out from the plasma around the black hole in the form of the light that we detect with the Event Horizon Telescope. But it can also, radiative transfer can also occur by convection, or energy transfer can also occur by convection, which is, you basically put some energy in a can and you pick it up and you carry it someplace else. So that's, or advection of energy, which is how convection works. And then another notion is that energy can be transferred by conduction. Okay, so all of those things are going on in the plasma around the black hole. Now, when you get energy out of the black hole and make those jets, That is probably due to electromagnetic fields. So it's a form of radiation, but it's a very, very, very low frequency form of radiation. So it's like setting up a wave in the magnetic field that has a period of many, many hours. And the black hole spins the magnetic fields around, and then that carries off energy from the black hole. Okay, was there another question? Yeah.
One question.
Earlier, I believe you mentioned that a black hole can escape its galaxy, so I was wondering if that would be possible.
So the question was, can a black hole escape its parent galaxy? So that is a topic of current research. So let me give you an example of a process that might lead to the escape of a black hole from its parent galaxy. So galaxies merge all the time. Okay, so we have a neighboring galaxy, Andromeda, which is rushing toward us at 100 kilometers per second. And eventually its central black hole is going to run in and merge with our central black hole when the two galaxies merge together. So the black holes are going to merge. And the last phase of that merger is driven by something called gravitational radiation, so ripples in the gravitational field set up by the motion of the black holes. And when two black holes merge, they can release linear momentum in the gravitational field. So it's as if, someone's sitting on the black hole and throws something off in one direction, and then the black holes recoil. Okay, and the throwing off in one direction is in the form of radiation. So there's no baseball involved, or basketball or what have you, but there's still a recoil. And there are simulations of this process which show that under very special circumstances, if you arrange the black holes and their spins just right, then the recoil can be pretty big. And the recoil can happen at speeds of as much as 1,000 kilometers per second. Okay, so that's really fast compared to the speed with which stars go around the galaxy. And if that were to happen in the center of our galaxy, it might lead to the black holes running away and becoming unbound. It's somewhat unlikely to happen in our galaxy because, again, the configuration is very difficult to achieve, and there's this dynamical friction which tends to slow things down. But when you have small galaxies that merge together, if they have black holes in them, which is, again, a topic of current research, then it's easier for the recoil to achieve a speed that would let you escape from a smaller galaxy. Yeah.
So when does our galaxy, or black hole
You
merge
want to-
with Andromeda?
When do we merge with Andromeda? Let me, I don't remember the number, but I can work it out for you on the spot. So Andromeda is about 750,000 parsecs away. And it's moving toward us at about 100 kilometers per second, which is about a parsec per million years. And so if I divide, let's see if I can do this. So it's like a billion years in the future. Yeah, a couple billion years in the future. So I think I've done that right. Does anyone, did I do that right? Did I get it? Okay. Okay, so it's a couple billion years in the future, and you and I don't need to worry about that. And even, I mean, it's hard to convey a sense for the vast range of timescales that the universe shows us. But even the solar system, even the sun, only has a finite lifetime. So a lifetime of maybe 4.5 billion years. And so around that time, the sun will be starting to get old. And when stars get old, they swell up and they turn red, just like people. And And so the solar system at that time will be different from what it is now. Okay.
Hey, wonderful. Charles, do you have time for one last question? I see someone with their hand
Sure,
up.
and I'm happy to talk to people afterwards.
Okay,
as well.
sounds good. Last one, and then
Yeah,
we'll.
I'm sorry, I
end
said
this
I was going to get to you, and I didn't. Yeah.
So you mentioned charged particles orbiting the black hole. Is that process similar at all to that of an electric motor?
So the question was, there are charged particles orbiting the black hole. Is it like an electric motor? There is an analogy that has been drawn, and there are certainly currents that are set up in the plasma, in the ionized gas around the black hole by its motion around the black hole combined with magnetic fields. But it is not a straightforward analogy. So people also talk about a generator. So a generator is an electric motor run backwards, and it's probably closer to that. So you have a spinning object which sets up currents and extracts energy from the black hole. Okay, I'm happy to take the question, but I don't know if we should.
I think maybe for everyone
Yeah.
else, we can wrap up now,
Yeah.
and then if people have additional questions, they can come up here, Charles, if you're happy to answer questions. Well, so first of all, let's thank Professor Gammie for a wonderful talk. And thank you to the audience for great questions as well. A reminder that if you're interested in being on the email list for Saturday Physics for Everyone, to sign up on the table outside here. I believe the next Saturday Physics for Everyone talk is going to be 2 weeks from today. You can, of course, visit our website to see all the different topics that we'll be covering this semester. So thanks, everyone, for coming, and we hope to see you soon at future events. Thanks, everyone.
Thank you.